All right, it's 4:01, I guess. All right, hi everybody. I hope you're doing well. I'm Nick. For those of you who don't know me, I'm one of the TAs here for Calc 3. I hope you're staying safe and all that. So this review session is kind of be a little bit, what we're going to do. I have a whiteboard that I'm going to be using. I'll be posting this online afterwards. So what I'm going to be asking you to do, if you can, if you want to ask a question, just so we can kind of have some sense of assembly here, if possible, you can either, I think we have enough people here, we have 18 people or so. If you have any question, if you have a question, if you just don't mind just unmuting yourself really quickly and then kind of, going from there. If we have a lot of people that are asking questions and want to ask questions, I'll probably just ask you if you have anything in the chat, just kind of respond something in the chat. I can go over that too. I have all of the midterm, mini exam files. I can pull those up. We can go over any problems you want there. I can talk about just general concepts. Really anything you want me to talk about, I can. So with that in mind, if anybody wants to, ask any questions, have at it. Does anybody have any questions that I can answer?
Can we go over question 1 on the that participation assignment that you gave us for chapter 14?
Yeah, we can go over that.
It was like the limit question.
Yep. I could talk about that. 1 second. So for those of you who don't, let me actually just pull up my whiteboard here. And we can go from there. I'm going to start sharing my screen. Go ahead and do that. Okay. So, yeah, there we go. Okay. I will try to make sure that this whiteboard will also be publicly available afterwards. So if you want to just check it afterwards, that we can do that too. So the first question we kind of discussed here is this limit problem, where I have the limit as actually, I think this is, I lied. This is x going from 1 to 2 of the sine of x minus 1, y minus 2, divided by x minus 1 squared minus y minus 2 squared. Here. Now, in the problem, specifically, in this kind of question here, I ask just in general here, just in general, I asked, at least I want to take a couple different limits. I want to take when x is equal to 1 and when y is equal to 2. I want to see those limits and just kind of evaluate those. So what is actually happening here? Just physically, what is actually happening here? And when we're thinking about a limit, we have to be very, very careful. So I have on my xy domain here, I have this function, this function here, I'll name this, you can name this function f or something like that. And what I can find is I'm trying to find the limit at the point 1, 2, up here. Something like this. Now, we can see, I hope you can see that if I plug in 1, 2 here, this denominator here is going to become 0. I'm going to have a 0 over 0 kind of aspect there, which can be an issue. So to find a limit, I can try to see if I can find a limit here, trying to do some different techniques. And in this case, what you have to be very careful of is the limits that I do take have to be going to the point specifically. So for instance, I say here, you cannot take the x-axis and the y-axis here. It does not make sense to do that. Because if I go on the x-axis here or the y-axis, I'm not getting to the point 1, 2. So you have to just be conscious of that. If you have a limit that is going to a different point, right, that's not the origin, you want to go on lines that approach that point specifically here. So in this case, we do have that I'm going to take x to be equal to 1. So x to be equal to 1 is this vertical line right here. And I'm going to be going down like this at this point. And again, the idea for finding the limit is I have to find that all directions going to that point all directions going to that point do have the same limit. If they don't, I know the limit does not exist. So if I take x to be equal to 1, my goal always in these limit problems is to convert my two-dimensional limit here to a one-dimensional limit. And this is a really subtle point because we have a lot of different, different techniques really to solve, one-dimensional limits. Two-dimensional limits, we have a little bit less so of them. So if I'm going to be able to doing this, what I'm going to do is if I'm on x to be equal to 1, I'm going to set x to be equal to 1, right? And what that's going to mean is my limit now is just going to be going from y to be 2. Y is equal to 2. So basically what I'm saying is I'm keeping x constant and I'm going down to c, or even going up. It doesn't actually, this actually tells me either way in this one. And so saying as y goes to 2, what's happening? And if I plug x equal to 1 in, I get sine of 1 minus 1, y minus 2, divided by 1 minus 1 squared, 1 minus 2 squared. Now, what do we notice here? We notice that this numerator here is, a little bit, it's going to be 0, this entire component here. So I'm going to have 0 times y minus 2, which is going to be 0. So this comes out to just be the limit as y goes to 2 of sine of 0 divided by y minus 2 squared. Sine of 0 is 0. So this limit is 0. Here. Now, what does this actually mean? This means that if I'm on this line at all, actually, if I'm on this line at all, the entire time my function is going to be 0. So that means that the limit has to be 0. In a similar way, I asked the question, okay, let's take the next logical step here, which is another horizontal line going through it, which is just y equal to 2. There's something like this line right here. And again, this means that x is going to be constant. So now I'm keeping y fixed, and I'm moving x to that point. In the same exact way, if I do that, y equal to 2. As you can probably see, this limit then will just be equal to the limit as x going to 1 of sine of now x minus 1, 2 minus 2, divided by x minus 1 squared and 2 minus 2 squared. Again, we would get the same exact issue. Sorry, not 0. It's equal to 1. And this top part here would be sine of 0 again, which would be x minus 1 squared. And again, this would be equal to 0. So this again means that if I'm on either one of these lines, on this vertical line or this horizontal line, I'm going to be equal to 0. Now, the last question we kind of asked for this is, does this imply that the limit exists? And the answer is no. And why is that the case? Because I would have to check literally every direction to get there, right? I have to check every direction to kind of get to this point. I have to kind of go through all lines, right? I have to kind of go in any direction that I want to get to that point. All of these directions have to get to there at the same exact height. If they don't, the limit does not exist. To show that this limit does exist, honestly, it's actually a pretty complex process. I think we would probably have to use the squeeze theorem to kind of show that this limit exists, which is not really what the question was asking. All I'm kind of trying to show there specifically is saying, okay, take x equal to 1, take y equal to 2. Can I then say the limit exists? You can't, because you do have to check all different limits to get there. It has to be true for all lines and all of that. So we have to kind of make some different, we would have to find that this limit actually exists. We would do a lot more work to get there. Does that make sense, Shoni?
Yeah, it does. Thank you.
Okay. Anybody else have any questions about that specifically here? Somebody did ask really quickly, are we ever going to say that limit exists for one of these problems? Yes, you can do that. There are limits. A lot of times the most beneficial thing to do, actually, if I'm not mistaken, there's actually a couple of problems in one of the practice exams that we do actually have limits that do exist. The best techniques there to show that the limit exists, at least in our cases here, we have a couple of things like conjugate, multiplying by conjugates in the same exact way that we did in Calc 1. So if I had something like, an x minus y on the bottom, yeah, so like I think let me at least go from there really quickly. Hold on one second. I went to the wrong file. Let me actually see. So I think actually you can, in this problem specifically, this limit does exist. Actually going through that. You actually can do this. And that's it. I don't think you would be asked that question here, actually, that one. Because it's actually really, squeeze theorem is a little bit too complex here. So you, question 2a, for instance, I can actually talk about that one. So the limit here as xy going to 1, 1 of xy minus x squared over the square root of x minus the square root of y. We can at least do this one here. This guy right here. This is the one that we'll do to kind of show you that a limit does exist here. So if I start to try to figure out this limit here, right, you can start to, if you wanted to, at least initially, right, to try to figure this out. You kind of draw out your schematic again. Kind of draw out this schematic here, at least to see where this limit is, right? We have this 0.11 here, which is up here. And I want to see if this limit exists. So the first thing I should do is be very, very, very cautious and take some very simple roots there. Take some very simple roots, as we kind of just did in the last problem. So the first things I would suggest doing are maybe going in the vertical direction and the horizontal direction. In that case. So this line is x is equal to 1. This line is y is equal to 1. So I can again do the same exact thing as I had done in the previous problem. If I take x to be equal to 1, this then comes out to be the limit as y goes to 1 of y minus 1 over 1 minus the square root of y. And that comes out to be there. And here what we can do to show that this limit exists, or to show what this limit is specifically, is, if I'm not mistaken, so I can't plug in 1, I have to kind of do something else here. I think we would probably want to multiply by our conjugate here to kind of show that this limit exists. At least that's in my head what we should probably do. So if I was to do that, I want to multiply both the top and bottom, and I think this is probably the technique that we will show to, I guess, eventually show that this limit does exist, if this does. What we do is we multiply the top and the bottom by the conjugate. And why do we do this? Well, this gives us a way to, get rid of maybe the square root on the bottom, at least there. So kind of just going through this, we would get y minus 1 here. Up here, we would get 1 plus the square root of y. On the bottom here, if I multiply by the conjugate, what actually happens is this becomes 1 minus y. Because I would do 1 times 1, and then the mixed terms, the o and the I of the FOIL terms cancel, and then I'm left with the square root of y times the square root of y, which is equal to y, which is just equal to y. And so why do we do this? Well, in this case, if I'm able to do this now, here, it's the limit as y goes to 1. This now allows me to see if I can actually cancel these terms here and here. If I put a negative out in front, these terms are exactly the same. So if I put a negative out in front and flip these and kind of rewrite this really quickly, 1 minus y, 1 plus the square root of y over 1 minus y. These terms cancel now, and what's nice is I can actually evaluate this. Because now this is a continuous function and I'm able to evaluate it. So this just becomes -2. Just plugging that in. So the method of conjugates here is, we can kind of see maybe that the method of conjugates might help us out in the long run. In the same exact way, you can do the x-axis as well, I think, here too. So we can at least take a look at that to kind of show you. So if I take y equal to 1 now, I want to move this down a little bit more. If I do y is equal to 1 now, and I do this limit now, it will be the limit as x goes to 1 of x minus x squared divided by the square root of x minus 1. Again, I see here that I probably want to use the conjugate technique because I see the square root aspect here. So again, to find this limit, I'll probably want to take the conjugate. So we would multiply it by the square root of x plus 1, and this top here, square root of x plus 1 as well. This conjugate method allows you to, the big thing about this conjugate method is it allows you a lot of ways to cancel things out of the denominator because of things you can find on the top and the bottom are similar, and so you can cancel them out. And so here you would get that x minus x squared, square root of x plus 1. On the bottom here, you would get the square root, you would actually get x minus 1. I'm sorry, yeah, this is a minus sign here. You should do that, minus. And this is going to be x minus 1. And now you might say to yourself, well, how do I start to cancel things here, right? How would this actually work? Well, as you can see here on the top, I can actually factor out an x from this term. I could factor out that x and maybe flip it. Maybe I could factor out a negative x just to kind of show you. Negative x here, this becomes a negative 1. This becomes a positive x. In that case, x minus 1. And so if I see this, these two terms, this term and this term is going to cancel. And so this becomes the limit as x approaches 1 of negative x times the square root of x plus 1. And again, if I plug in 1 there, I'm going to get negative 2. Again here. So what does this say then? Kind of zooming out, kind of the big picture here. I've taken this limit, and now I'm saying to myself, okay, I have found that going horizontally and going vertically get me to the same limit value. This doesn't show me that that limit is, but what I've done here, and this is actually a really important thing to see, regardless of what x I picked or what y I picked, if I did this, I would use the same technique over again, right? What I did is I multiplied the conjugate in the top and the bottom, and I actually I did the same technique. So if you do the same technique for these two, you should maybe think to yourself, can I extend this? Can I do this for all of them, right? I've done it for one, I've done it for the other. Maybe I could do it just in general. And now that's what we're gonna do instead. So what I'm gonna do now is I'm gonna see if I can prove this entire thing using the same exact method that we just did. And now I get x, y, what's it? It's xy minus y, it's x squared divided by the square root of x minus the square root of y. Same method here. I'm now going to multiply the top and the bottom by the conjugate. The conjugate here is the square root of x plus the square root of y. By the square root of x plus the square root of y. Okay, great. So now what happens here is so the same thing probably happens with the origin. You want to be a little bit careful though. I don't know if the limit will exist at the origin at the moment here. So we'll tackle that in 2 seconds. I'll have to kind of see. I think it probably would work also for the origin, but we have to kind of see. So in this case, if I do this here, this top guy, I'm going to factor out an x in this top term right here, because I kind of see that that's kind of what I've done in these parts over here. I factored out, at least in this one, I factored out, right? I factored out an x. I might want to do that. So I'm going to do x, y minus x, and then I get the square root of x plus the square root of y, divided by, this becomes x minus y. That's what that comes out to be here. So what's nice here, if I see this, is that these two terms, this top term here, right here, and this bottom term, again, will cancel each other if I just make a negative, yet again. So this becomes the limit as xy goes to 1, 1. These two terms cancel, and I'm left with a negative x times the square root of x plus the square root of y. And there you go. And now I'm able to just evaluate it because this is a continuous function. So I can just actually plug in 1, 1. And again, I would get that this is negative 2. And so therefore, that is my answer. So kind of going back, and I think the person that just asked about if this works for the origin, I think it does, because I wouldn't change my method regardless. The origin would be at 0 at this point. So nothing really changed. So again, kind of zooming out the picture here, this is at least my opinion on how to do this. At least in all these types of problems here. Yeah, so in every single one of these types of problems, regardless if the limit exists or does not exist, regardless of that fact, what you should do at least is, if it's not continuous already, if you can't just plug it in, check out the easiest directions to go in. In this case, horizontals and vertical lines are probably the easiest things. If you see a technique that you did that is actually kind of different, at least to solve the one-dimensional limit in both of these. If you see a common thing, for instance, we did both the conjugate, we multiplied the conjugate on the top and bottom for both of these. If we go ahead and do that twice, we might say to ourselves, okay, can I do this for all of it? Can I just do this in general? Maybe I could prove it that way. And so therefore, because I found that this limit, I proved this limit here. I've shown that regardless of the direction I've picked, just doing by this square root of x times the square root of plus the square root of y, multiplying the top and the bottom with the conjugate method, I've shown that this limit does exist. So regardless of direction I go in to this limit will always go to -2. And so therefore, that's how I kind of go about these types of problems. If you do have, I really would suggest, usually sometimes the ways to prove these, maybe use polar coordinates, right? If you have an x squared plus y squared, that would be a polar coordinate one to kind of go for. If you had something else, right, you might want to try some, maybe some other methods too. If you go to polar coordinates, you're probably going to have to use L'Hopital's rule here. Yeah, and so if this limit was had a continuous, let's say I was going as x, y going to 2, 5 or something like that, this function is continuous, so you can just plug it in. So don't overcomplicate it. Always just check to make sure that the limit actually is, the function value is actually not defined. Because if the function is defined, just plug it in, and you're good to go. Okay. I hope that answers your guys' questions with this. So in this case, my limit does exist. Yes, in this case, my limit does exist, and it is -2. That's my answer. Okay. If there's no other questions on that here, we have a request here to do question 8 from the mini exam review. Are you talking about this one, Isa? Is this one specifically the one with the level curves?
Yeah, that's the one I'm talking about.
Okay, great. So the whole problem, A and B here?
Yeah, well, I started with doing A and I didn't come far, so.
Okay, that's cool. We can do this regardless.
Yeah.
Yeah, that's cool. So this is the next problem that we'll do here. Now, the first thing I want to say specifically about these types of problems, I guess the first thing we would want to do is just realize, what are level curves? And I'm going to just define this again, what the idea of a level curve is. So the idea of a level curve, all of these blue lines, what it basically is saying is I have this function f, and imagine you have a mountain, and I am just slicing the mountain at a certain height. I'm slicing that mountain, and where are all of the points at the same height, right? That's kind of my goal. Where are all the points at 1,000 feet above sea level? Where are all the points at sea level? Where are all the points, 1 foot, 2 foot? What are these kind of functions where are the heights of these functions? And each one of these lines right here, this tells me, at least each one of these contour lines tells me exactly where all of my functions, my function height is the same. So if I stay on a contour line, my function height is always the same. Okay, now let's kind of start to talk about, I guess, in this case, directional derivatives. Right? The idea of a directional derivative is if I give you a function and I evaluate that function, I try to find the directional derivative. The goal, again, of a directional derivative, it just as a derivative in general, is to figure out the slope of the function. In this case, in 2 dimensions and in higher dimensions like this, slope is not really well defined, so I have to pick a direction of the slope that I'm really talking about. That's why we get the idea of the directional derivative. So what this tells me is I am going in a certain direction. I tell you a direction that I'm walking in. Imagine you're, just in general, just going in, just in a certain direction. The directional derivative tells me how fast my function is increasing as I move in that direction, or decreasing, depending if it's negative or positive. And if it's 0, right, that means my height's not changing. So my directional derivative is 0. That means I'm staying on a contour line because my height is not changing. So with this in mind, let's kind of tackle this. So I have a contour plot here. I hope everybody can see it. And my goal here is to figure out these directional derivatives. Just trying to figure out, do I have a limit? Does this exist? Just in general, is this positive, negative, or 0? It's very tough for us to figure out otherwise. So let's first off start to think about u here. U, the direction is 1 over square root of 2, 1 over square root of 2. The 1 over square root of 2, 1 over square root of 2 is, just as a reminder, just right as a 45-degree angle. So if I'm taking, for instance, Q, this would be it would just be in this direction here. I'm walking in this direction. So I'm going to first off start with P here. Okay, if I walk in the direction of P, right now I'm at a height of 0. If I walk in the direction of U, which is in this direction, very, very instantaneously, right there, am I changing my height at all? I'm not, because I'm actually staying at a height of 0. I'm just moving in this direction. So because of that, the directional derivative going in the direction of U will be 0 at a point P, because my height is not changing. My height is not changing. My function height is not changing whatsoever. So because I'm going in this direction, my directional derivative here would just be 0. Now, if I take Q and I go in the same direction this way, well, I'm at a height of 2, right? And I'm going in this direction. We assume that in between contour lines, I'm always increasing my height. That's what we kind of have to assume. We have no other really options to do so. So what I do is I go to Q, I move in this direction here. If I'm moving in this direction, I'm going from 2 to 4, getting closer to 4, which means that my height is increasing. And so therefore, because of that, my height is increasing, and therefore this is a positive. Okay. And lastly, for R, I'm going in this direction again, in this guy. And if I'm going in this direction here, well, I need to think about this. Well, if I'm going in this direction, I'm around -1-ish, and I'm getting closer to 0, which again means I'm increasing my height. And so therefore, because I'm increasing my height, that means that my directional derivative should be positive. So in this case, this should be 0, positive, and positive. Now, if I'm talking about direction V is 0, -1, which means I'm going straight down. Okay, so let's tackle each one of these individually again. If I tackle P here, and I go straight down. Now, it seems like it's actually kind of a weird one here, but let's kind of look at this. If I'm at P, I go straight down. It is very instantaneous. The directional derivative is very local. You have to be pretty careful with that. It's very, 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 very local. That means if I move a little bit, my directional derivative changes again. The rate at which it changes. So you have to be kind of, you have to be kind of a little bit careful. So I'm going in this direction. I am moving towards the positive side, because in between 0 and 2 here, all of these values inside of here are between 0 and 2. So if I move into this area, my function height will be positive. It will be positive. It will be greater than 0 because I'm in between 0 and 2. Because of that specifically, I do have that this directional derivative will be positive, because I'm going from 0 to something as a positive value. I'm increasing my height as I move in that direction. Now for Q, this is a little bit interesting too. So if I move in the direction of Q, just in the direction of Q, at the point Q, if I move just straight down in this direction, you might say to yourself, well, I'm going from 2 to 0, so this would probably be negative. And the thing is, you have to be very careful here, because this is somewhat misleading how I'm kind of doing this. You need to think about this very, very, very localized. So as a reminder, if I move tangent to the contour line that I'm on, that means I am staying on my contour line. In the same way here, this is a line. So if I just move in the direction of the line, I'm going to be tangent to the line. Right? That direction is tangent, because the tangent to a line is just the slope of the line. That makes sense. But here, if I move in this direction, that direction going downwards actually will continue making me go on that contour line. I'm going to be staying on that contour line, which means that my directional derivative is going to be 0 because I'm not changing my height. So this is a really important point. If I'm moving tangential to the contour line that I'm on, I automatically know that my directional derivative must be 0. Just as a fact. Because again, I'm not changing my height really here. If I'm going here, and again, I have to think about this very locally, because if I go in this direction here, and then just try to change my directional derivative is going to change again if I go on a different line, just a slightly different point if I move in that direction. So don't make your lines too long when you're thinking about these. Make these just as very small as possible, just so you know the general idea of the change of height. And lastly here, for R, if I just go straight down, I hope it's pretty nice to see here that this is actually a little bit nicer, where I'm going from -1-ish to, I'm going towards the -2 contour. So because of that, I'm actually going towards -2. And that's kind of my idea. So therefore, this is going to be a negative in this. So up here, this should be positive, 0, and negative there. And so that's how you figure out the directional derivatives more. Now, as well, we say in the diagram above, sketch the gradient of f divided by the norm of f at p and at q. Okay, so what is the relationship between directional derivatives and contour lines? That's actually a really important thing to kind of think about. So I'm going to go back to my whiteboard really quickly to kind of show you something. I have lost my little stylus. There you go. So if I think about this, again, the formula for the directional derivative here, kind of going to this, is just the gradient of f dotted with u, right? That's my goal here. The directional derivative is the gradient of f with the dot product of u, which u is my unit vector that I'm going in the direction of. So what's kind of interesting is, let's say I want this to be 0. What does a directional derivative being 0 mean? A directional derivative of 0 means that I'm not changing my height, which means that I am staying on my contour line. That means the direction u, let's assume that u is the direction of the contour line. What does that then mean? Well, I have this dot product here. This dot product being 0 means that the gradient and u have to be orthogonal. So u is in the direction of the contour line because my directional derivative is 0. So my height's not changing. And it has to be orthogonal to the gradient. So that means the gradient must be orthogonal to contour lines. And that's a really important fact to know. The gradient is orthogonal to contour lines, or just any level curves, just in general. So if I'm back here, and I'm back here, and I'm trying to figure out what the gradient is. The gradient also gives me the fastest rate of, gives you the direction where my height is increasing the fastest, right? The maximal rate of increase. Well, orthogonal lines, an orthogonal vector would be either in this direction or in this direction here. But I know if I go in this direction, I'm going to be going negative, which doesn't really make sense. So because of that, I'm going to be going in this direction here. And this line right here, if I draw this vector going in this way, going from P out to here, and making sure that this here is actually a norm of 1. This means that my magnitude is going to be 1 because it's dividing it by the normal vector, right? Dividing it by the unit, the norm of it, the magnitude of it, gives me a unit vector. So I want to just make this a magnitude of 1. And it's going to be going in this direction because it's orthogonal. In a similar manner, because I'm on a contour line here, I'm going to be, if I want, I can either go this direction or this direction to be perpendicular. Going in this direction would make me go down, so I don't want that. I want to go up, and so therefore I'm going to be drawing my line going on these x-axis right here. And those are the ways that I would draw the gradient. This is really hard to draw the gradient because I'm not on a contour line. So I really wouldn't be able to ask you that because I just don't know what the contour line at that point is. But P and Q, because I'm on a contour line, I can draw that. So you need 2 things. 1, it has to be orthogonal, and 2, it needs to be in the direction of maximal increase. So it needs to be increasing the height. If you were asked to find the maximal decrease, drawing that, you would go in the exact opposite direction, because we know that the direction of maximal decrease is just the negative of the gradient. That's kind of how you do this problem 8 here. And kind of just overall general ideas of directional derivatives and contour lines, just and gradients when you're thinking about this visually in that level curve. Does that make sense?
Yeah, thank you.
Cool, no problem. Yes. Cool. So that's kind of what I'm doing there. And that's the idea. So just making sure that you're always kind of just careful with that. Yeah, so that's the solutions of the practice quiz. Yeah, so does anybody else have any questions about this specifically here? Okay, so I have a request to do a problem about drawing level curves, and then I will go ahead and do something else on top of that. So I'm going to just do a problem with drawing level curves there, and then go back. So I'm going to go back to my problem. I actually have a problem on this here, in this problem right here, in this one that I created, where I've considered this function, and I'm going to draw the level curves of this function here. Okay. So I have a function f of xy is equal to the square root of xy minus 1. And my goal here is I would like to draw the level curves for k equal to 0, 1, and 2. Now, if I'm going to be drawing level curves here, what I want to do is the goal of level curves is where are all my function values equal to some number k, right? Where is f of xy equal to k? Now, how do I do that? Well, you can do this very, very generally, actually, if you wanted to, where I could say, okay, well, if this is going to happen, I'm going to say k is equal to the square root of xy minus 1. And if I do that, well, I can solve for x and y. My goal is to get something, because I'm going to be drawing something on the xy plane. I would like something y equals or x equals or something like that to help me out. If I can do that, that would be great. So squaring both sides, we get k squared is equal to xy minus 1. Moving the 1 over, I would get k squared plus 1 is equal to x times y. And then from there, what I can do is I can actually divide out by x here. And so I get y is equal to k squared plus 1 over x. And for all k, this is going to be what it's going to look like, just depending on different k's that I plug in. This is going to look like, we'll draw these out, but depending on which k I have, this is going to be the level curves. So just as an idea here, we're going to take, here, I'm going to do k is equal to 0 first. K equal to 0 would just get me y is equal to 1 over x. I know how to draw that. That's good. And making sure we go on this other side here. So this is k equal to 0. Whenever you're drawing level curves, you want to make sure you're labeling properly. Make sure you always say, what the function height at that point is. It's really, really helpful. You're not going to have colored pencils on the exam, but you can at least still, label them properly. Similarly here, I now have, I'm going to use purple, k equal to 1. If I do k equal to 1 here, I'm going to get y is equal to 2 over x, which is cool. Again, this is kind of the same exact idea, just a little bit higher. If I want to be really, really particular about it, I could say that there's a point here that's 2, 1. 1, 2. My bad. 1, 2 here. And so this is k is equal to 1. And then lastly, I have to also go on this bottom one here. There's also this bottom one here. Other one. And lastly, I have k is equal to 2, which is going to just be then, 5 over x. And so if I do that, that's going to be even a higher one. K equal to 2. And k equal to 2. That's how you draw level curves. Sometimes there's some very interesting differences when I go from like a positive k to a negative k or something like that. This really, really depends kind of on the problem at hand. You also want to be very careful too when you're drawing level curves that you see what I did here at this point right here. I divided by x. Now sometimes that might not be the best decision because you actually might miss something. So let me just at least talk about that relatively quickly, just so I can show you what I mean by that. Say I have the function f of xy is equal to x times y, something like this. And I want to find my level curves, right? You get k is equal to xy. And again here, you would, let's say I want to try to find, if I do the same exact thing I did over on the other side, I'll get y is equal to k over x. Right? Not too bad. Now, let's say, for instance, I wanted to find what happens when k is equal to 0. Well, if I plug this in here naively, I would get that this is just y equal to 0. Right? So my curve would be something, that x times y, right? It would just be y equals 0. It would just be this line. But you have to be very careful, because what actually happened, if I go back to this guy, right, this exact formula, and I let k be equal to 0 there, I get 0 is equal to x times y. Which means that this implies that x is equal to 0 or y is equal to 0. Right? So if you see that, I would actually get I would get another solution. I would get this other one here. So you have to be careful that you're not dividing out an answer here specifically. If you're dividing out an answer, are you dividing out just in general? Are you gonna miss a solution? Are you gonna miss a line? Are you gonna miss a curve by doing that? You always just want to make sure that you're doing that prior to dividing out by that. Always want to make sure. Other than that, this is kind of how you would do level curves, just in general. You're setting equal to k, and then plugging in for different k and seeing what happens. You could do this generally. You could actually just every single time, if you wanted to, plug in another number and go for it. But if you see a pattern, it's might be a little bit nicer to kind of write that pattern down. Okay. Any other questions about this? Okay, so if there's no other question about that, then what I'm going to do, that I have a problem for 3a for DJ's part there. So are you talking about this part, Sanjita, here, problem 3?
Yes.
Yes.
I was able to do until only fx, but then I had trouble doing like fxy.
Okay.
Like simplifying and all. I got stuck.
Okay. Yeah. So it's a little bit of a tedious question. I will give it that. So let me go ahead and try to write this down a little bit, at least to kind of show you how to kind of go about it. So I have here, I have a function f of xy is equal to e to the x squared plus y times arctan of xy. And I want to compute fxy of 0, 1. Okay. So this is kind of a fun one. It's a long one, but it brings up a lot of really interesting points. The first thing we need to know, and especially with mixed partial derivatives, is to remind ourselves, what is Chloros Theorem? And what does Chloros Theorem say? Chloros Theorem is actually really nice. Chloros Theorem says fxy of 0, 1 will equal fyx of 0, 1 only if f is continuous at that point. And we see here, if I plug in 0, 1, it's continuous, arctan of 0 is defined. So this is continuous. So therefore, we can calculate this either way. We can either go y first and then x, or x first and then y. I think personally there's not really a big difference because there's a lot of symmetry here. So since there's a lot of symmetry here, I don't know specifically which direction I would like to kind of go in instead. So what I'm going to do here is I'm just going to tackle x first, just in general. Kind of go from there. So let's tackle fx first. This is the first derivative with respect to x. We see here that I have a function multiplied, a function of x times a function of x there. And in that case, I'm going to do the product rule. So the derivative of e to the x squared plus y is just 2x, e to the x squared plus y, arctan of xy, plus the derivative of arctan with respect to x is 1 over 1 plus xy squared. And then I have to do the chain rule because I have to multiply by the derivative of xy with respect to y. So I would then get e to the x squared plus y multiplied by 1 plus xy squared. The derivative of xy with respect to x is y. So that would be the derivative there. Here. I can actually simplify this a tad by factoring out the e to the x squared plus y. if I do this, I would get 2x arctan of xy plus y over 1 plus xy squared. It's something like that here. Okay, so now I have fx, and now I need to take this derivative with respect to y. In doing this, again, we're going to use product rule. So again, what's going to happen? I have this function here with respect to y. The derivative of this function with respect to y, this e to the x squared plus y, does not change, right? Because of the derivative with respect to y, that will just be 1. So this is still the same thing. So I actually have this whole thing. I'm going to rewrite this thing again. xy plus y over 1 plus xy squared. Something like that. And now I do a plus here. And then what I'm going to do is I'm going to take the derivative of this inside. The derivative of this inside here starts to get really fun. So this guy right here, I have to use the product rule. I am going to be very, very conscious and go on a different line. So I'm going to e to the x squared plus y. Factor that out. And then I'm going to do the product rule here. The derivative of 2x is just 2. Arctan of xy. Plus the derivative of arctan with respect to y. Oh, sorry, I lied. Bad Nick. We are doing this with respect to y. So 2x is a constant, right? 2x is a constant. So the only thing I have to take into consideration here, this is not a product rule. This is just honestly the derivative of arctan with respect to y, which again would just be 2x, and I would do 1 plus xy squared. The derivative of this with respect to y, then I would have an x on top. Because the chain rule here, the derivative with xy is going to be x. Then over here, this guy, I'm probably going to want to use quotient rule. Probably the best way to do it. So I have my numerator and I have my denominator here. As a reminder, what the quotient rule is, if I have f over g, if I take this derivative, I would f prime g over g prime f divided by g squared. So the derivative of this top guy is just 1. So I'll just be left with the denominator minus g prime here. The derivative of this is, I'm going to have y. The derivative of this guy is going to be 2 times xy. The derivative of this with respect to x is, with respect to y, is an x. I'm going to pop out the derivative, I'm just going to pop out an x because the derivative of xy with respect to y is x. I have said xy way too many times in this problem so far. And then on the bottom, I'm just going to square it. Cool. So in this problem, let's kind of just remind ourselves how we're kind of doing this. Right here, what I did is, again, I did product rule with respect to y. So the first part was the derivative of this e to the x squared plus y, which was just, in this case, just e to the x squared plus y, and then left with the other function here. Now the derivative of the other side, this guy, the derivative of arctan xy with respect to y is 1 over x squared xy squared, and then I take the derivative of xy with respect to y, which is x. So I get, the derivative of this guy just inside of the chain rule here with respect to y is x. And that's why I get this popped out up here. Similarly, on this other side, I get the product rule. So the quotient rule. So again, I would take the derivative of y, which is just 1. And that's why I'm just left with the denominator at this part. Then I would subtract y, which is my numerator, times the derivative of the denominator. The denominator here is 1 plus xy squared. So the derivative of that is just 2 times xy. Using the chain rule, this becomes, again, I multiply this by x. If you wanted to see that instead, you could have written this as x squared times y squared, and then taking the derivative of that, where it's just 2x squared y. What I want to do. And then I'm left with the 1 plus x squared squared on the bottom. That's kind of the goal of this whole thing. And now I am not going to touch this anymore. I'm just going to plug in at this point. I'm not simplifying this. And if I plug in, I forget what my point is, at 0, 1? Here, 0.01. Well, these two values, the e's, are just going to be e, because it's going to be just a 1 on the top. E to the first power is just e. Now, this guy right here is going to be, this first part right here is going to be 2 times 0, so that's entire 0 right there. Great. Over here, this one is going to be 2 over 1, which is 2.
Excuse me.
Yes.
Is the Chloros is it supposed to be 0, 1, or is it 1, 0? Does it switch because you took the y first?
Oh, no, it is. I wrote it incorrectly. My apologies. Thank you. No, that is a very good point. I'm sorry. I did not realize that I was doing that correctly. Thank you very much for changing that. I'm on 0 there. So this changes a little bit of what I was doing here. So this then becomes 2 times 1 times arctan of 0. Over here, this entire thing becomes 0 because this is y. So this whole thing will just become 0 on this part. Then I'll have an e. Up here, I would get 2 times 1 divided by 1 plus 0. This part over here, I'm going to get then a 1 minus, well, this part right here, the y is 0, so that's going to just go away, which is great. And this is divided by 1 here.
I have a question really quick. So,
Yes.
wait, why did you change it from 0, 1 to 1, 0 now?
The problem is 1, 0.
Oh, okay.
Sorry.
Okay.
That was my clerical error. My apologies. Yes. The problem is 1, 0. All right, we'll stick with that. So in this part, well, what is arctan of 0? Right, that's the last thing I really need here. Other than that, everything else is just kind of writing. Arctan of 0 here, well, when is tangent 0? Tangent of 0 when my sine is 0, right? Which means that I need to be on my x-axis, which means that I need to be at 0 here. So that means that arctan of 0 itself is equal to 0. So this entire thing right here kind of goes away. And down here, I'm left with 2 plus 1. And so this whole thing comes out to just be 3 times e. And that is my answer. And so what is this actually saying? This is saying that the derivative of f with respect to x and then y, or with y other than x, at the point 1, 0, is equal to 3e. Whatever that value is, around 9. So it's kind of going back, remind ourselves of kind of how we do this. Again, Chloros Theorem is really important. There might be a much simpler way to kind of go about one of these problems. So, flipping the order of integration might not be a bad thing. Sometimes it might be much more beneficial for you to go one way than the other because it simplifies things greatly. But in this case, it really didn't. It was just a nasty problem just to begin with. And so regardless, you have to go through it. Just make sure that, you remember kind of your product rules there, your chain rule, your exponential rule, how to take arctan, a lot of good stuff in there. Even quotient rule. It brought back basically that whole chapter in Calc 1. Gotta go for that. So does that make sense, everybody? Anybody any questions about this specifically? Okay. So as a question there, somebody asked, is fxy equal to fyx? So that is actually always not true. Not always not true. It's a bad way to put it. Sorry. It is not always true. It only is true if the function is continuous at the point. So if I go ahead and honestly just calculate fxy at AB, this is only going to be true if f of AB is continuous. And this is due to Chloros Theorem. Right? This says that fxy is equal to fyx if at AB is continuous. So if you're continuous, then yes, you can kind of flip them. If you're not, you have to be very careful. It's not going to really be with anything that we kind of have to worry about, at least here specifically. But most of the time, you're able to just flip the order of integration. As works for as many. If I have something like f x zy, this could also be written as f x y z. Like I can flip the order of integration there if everything is consistent too. Yeah.
That's what I was about to ask. Will we see any multivariable like XYZ problems with Chloros Theorem?
I mean, you might be asked to take a third partial derivative. They would have to make it very simple because it's going to be very complicated to do that. I mean, at least just know that, I mean, if if there is a problem like that, they most likely will probably want you to recognize that taking the derivative in a specific order will probably be a lot simpler than others. I think that's probably what they would kind of be going at. So if I had something that kind of simplifies the problem greatly, that's kind of what we would want to at least to check out. So always just see to yourself, okay, if I'm all continuous, is there probably a simpler way to go about it? And the answer is sometimes yes. Sometimes if it's a lot of symmetry, like in this problem here, there was not a lot of symmetry between x and y, probably would have been the case. Question mark. Any other questions here? Okay, any other questions that I can answer? Any other questions?
Quick question, actually. So
Sure.
I know we did this problem a while ago. It was number 1 on TJ's review with the limits.
Yeah.
So what's like the main reason that we're setting x and y both equal to 1 and then solving when we could have just like multiplied the original limit by the conjugate in the very beginning?
Oh, so that was just a kind of a check for us to kind of, I guess the first thing you should kind of always do is just kind of see, is there a really simple way to prove that this limit doesn't exist? You know, I guess, you know, you always want to be cautiously optimistic about a limit and just kind of see if there's a really simple way, or maybe if you start to do limits, you can actually see what answer I should get at the end, right?
Okay.
I mean, that's kind of what I want to try to, that's how I would do it. Honestly, that's the way that DJ wrote that solution is exactly how I would go about it. I would honestly just check really simply in the x direction, the y direction, see then, okay, I see a similar, you know, a technique. I'm gonna now try to do it in general.
Okay, and if you get all the same answers, then they're gonna then the limit does exist.
Right. And if I start to see that maybe I can't, if I try to evaluate this limit, you know, using the conjugate method, and I start to realize I really can't simplify this a lot, you know, maybe I can go back to the drawing board and kind of figure out, okay, can I come up with a different direction? You know, that might admit me a different one, right?
Okay.
That's kind of how I think about it.
Also, so with the way that we did it, so let's say we set it x equal to 1, y equal to 1, and we get the same limits for both of them.
Mhm.
Is there any way that we can get the same limits for both of them, but then when we like do the original, it could give a different value? Or
if it does, something went wrong.
okay. Yeah,
Yeah.
that's what I was thinking. Okay. So
Yeah,
they should probably be the
something
same.
went wrong either in your way that you solved that limit, or in maybe you oversimplified that how you solved that general limit, probably.
All right.
Yeah.
Cool. Thank you.
Yeah, no problem. And that's actually why you want to check the original ones, just to make sure everything kind of lines up.
So
Okay.
should you check the original limit like that, and then if it doesn't give you something that you can like work with, then you do the where you set the y and the x equal to the numbers, or should you do that right away?
Unless you see something like, for instance, if I look at B, I immediately should think about, because I have x squared plus y squared, I'll probably automatically go to, you know, polar coordinates. Right? This is very similar. Like this one, I see here, like, okay, probably I should go to polar coordinates if this is an issue. Up here though, I don't really have, at least off the bat, I don't see like a general technique. It's actually much easier for me to see a technique when I go down to a one-dimensional limit. And so checking your horizontal and your vertical ways of going towards that point is a lot better, honestly, just because it gives me at least a sense of, okay, if I do prove a limit, what should it be? And if I don't prove a limit, you know, maybe I found a technique there going, okay, if I make this, you know, if I check this direction, maybe I get something different, or something along the lines of that. I usually like to just go, at least at the beginning, with just checking my horizontal and vertical limits, just to make sure I'm sane to myself, and to think about, okay, yeah, that makes sense. And that kind of goes forward. And then after that, I kind of think about, okay, what techniques can I use here? Kind of go forward.
Okay. Can we do B, do you think?
Yes, I have a couple of other questions that I have other people that are asking at the moment, but we can get back to B later, though. I'll be happy to do that later. That case. So we have a request here to kind of go over some from. Oh well, actually, Max, you actually asked from late chapter 14. That's actually what you were asking. So what specifically there are you thinking about?
Maybe a few of the gradient problems.
Gradient problems?
Yeah.
Okay. Do you have one in mind?
No, I didn't have any
Okay.
other one.
Yeah, give me 1 second here. I think, there we go. Whiteboard Fox kind of went on me. So I have a request just at least going forward here. I'm going to do some gradient problems. I guess, are you trying calculating the gradient or stuff with the gradient? I guess, what about the gradient kind of problems are you kind of looking for?
Well, calculating the gradients, like what we were just doing with the fx and the fy, right?
Right.
Like the partials. So I guess not that, but other things that you do with it.
Like using it to find a tangent plane?
Yeah.
Is that kind of what you're thinking about?
Yeah.
Okay. So, well, I could even think about this problem right here. Yeah, we could even do this problem. So I'm going to be looking at problem 7 from DJ's thing and also amending it a tad. So I have f of x, y, z here is equal to z times the natural log of x, y plus z. And I'm taking a look at the point 0, 1, 1, and I'm trying to find the directional derivative in the direction of 1, 2, 2. And then after this, what I'm going to do on top of that, no, where did it go? Help me out. And then after that, what I'm going to do is I'm going to find the tangent plane approximation, tangent plane to this at the point 1, 0, 0, 1, 1 here as well of this surface specifically here. It's actually causing me a little bit of issues at the moment, this whiteboard. Unfortunately, it's not really refreshing. Yeah, I can tell. Great. Good start here. So, help me out, please. Yeah, this website I bet has been unfortunately being crashed a little bit too much for the last couple of days. I apologize. I'm trying to get back to my point over here. Okay, so am I able to draw this now? Ah, there we go. Okay. So z natural log of xy plus z at the point 0, 1, 1. Let's see. Is that right? 0, 1, 1. Okay. What I'm going to do here is I'm now going to calculate specifically, if I do this correctly, I'm just trying to see something. X times y, yeah. So if I take a look at this surface here, and I would like to find a tangent plane to this surface at the point 0, 1, 1. Well, if I want to find a tangent plane to the surface, the first thing I should realize here is just to make sure that this point is on this surface. I can plug in each one of these points just kind of as a general check. If I find the point f of 0, 1, 1, this would then just be equal to 1 times the natural log of 0 times 1 plus 1, which is just equal to 1 times the natural log of 1, which is 0. Okay, cool. So that means that this point right here is on this surface, somewhere on this surface. So it's all of the points such that, you know, z times the natural log of xy plus z is equal to 0. All of that. And my goal here is to find my tangent plane to this surface. Now, I want to kind of get to the fact that how do I come up with a tangent plane, right? The tangent plane comes from just a plane equation. Y0 plus z times z minus z0 is equal to 0. That's how I write the equation of a plane. And my normal vector to the plane is ABC. So that's the vector that's orthogonal. Now, how do I then find my normal vector for this surface? What we can find is in the same exact way that, a normal vector, the gradient vector is always orthogonal to level curves, as we've seen in the past, right? We saw in the past that the gradient vector is always orthogonal to level curves. In the same way, the gradient vector is orthogonal to level surfaces. It's the same exact idea. So because of that, we know that the normal vector is going to be orthogonal to this surface. So we know that to calculate this, I'm going to name, oh, this is already named f, great. The normal vector here is actually the gradient evaluated at the point x0, y0, z0. Okay. So what you should do if you ever are trying to find the tangent plane, especially if you have this, first thing you should do is make sure that you have something like a function equal to a constant. That function then, this function right here, is going to be equal to your f. And what you're going to do is take the gradient of this as a three-dimensional limit, three-dimensional gradient, and then evaluate that gradient. And that is going to be your normal vector. So the gradient here, let's calculate the gradient just in general. The gradient, again, is equal to fx, fy, fz. And this here, with the derivative with respect to x here, is going to be a little bit interesting. So the z is going to go on top. The natural log is 1 over whatever's inside. And then I multiply it by the derivative of this inside with respect to x, which is just y. Okay. Similarly here, for the derivative with respect to y, it's going to be basically the same exact thing, just my function on top now is going to be zx instead. So z over xy plus z times x now, due to my chain rule. And lastly here, with respect to z, we're going to have to use the product rule, right? Because I have a function of z and another function of z. So if I do that, my product rule here, the first derivative with respect to z is just 1. So this becomes the natural log of xy plus z plus, and then the derivative of this with respect to z here, the derivative of this with respect to z is just 1 over this entire value, because there's no really chain rule that I really need to worry about here. So it's just z divided by xy plus z. And this right here is my gradient. You can utilize this if you want to find the directional derivative of something, right? Which is in problem 7. That's kind of what you should do, right? Find the directional derivative here. So the gradient of f at the point 0, 1, 1, we're going to plug this in. This first one up here is going to be, we see y times z, which is 1 times 1 divided by 0 plus 1. This right here, this y component here, the x is going to be 0, so this entire thing is going to be 0. And then similarly over here, we're going to get the natural log of 1 plus 1 over 0 plus 1. And we would get something, actually, if I plug this in, like 1, 0, and the natural log of 1 is 0, so this entire thing will be 1. And so this right here, this gradient vector, is my normal vector to my surface. And so therefore, if I want to write the equation to this tangent plane, just this equation of the tangent plane to the surface at this point, what I do is I take now the normal vector here, so a, b, and c is equal to 1, 0, 1. I would do 1 x minus 0, because that's my x component, right? Plus 0 y minus 1 plus 1 z minus 1 is equal to 0. And this is the equation for my tangent plane. I can simplify this even a little bit. Actually, drastically. This becomes x plus z minus 1 is equal to 0. I could even write this if I wanted to as z is equal to 1 minus x if I wanted to. You don't have to. So the goal of this here is just kind of coming back to what the idea of the gradient is. The idea of the gradient is it gives us a lot of different things. It gives us the maximal rate of change. or in the direction of the maximal rate of change. It gives us that direction. If I get that direction, right, that gives me the direction I need to face, that gives me where my function is increasing the fastest. In the same exact vein, this also gives me a normal vector to my surface, because it's orthogonal to level surfaces or curves, which is what this actually is. This right here is a level curve, a level surface. This is actually where all of these functions, all of these function values, f of x, y, z, are equal to 0. And so what this gradient tells me is it tells me where I'm going to get to the next level surface. You can kind of think about this as Russian nesting dolls, as I kind of had imagined this. I imagine different spheres, the outer, outer, outer. I want to get to the larger sphere. It's going to be an orthogonal vector that goes and points towards the other spheres. And so because of that, we get that the gradient is also a normal vector to our tangent plane. And so just calculating the gradient out, evaluating this at that point, and then just plugging this into the formula as we usually do for the planes. That's kind of the goal here for that problem. And the idea for gradients in that case. Yeah, that's cool. Does that make sense?
Can you tell about like how you were saying the gradient is orthogonal to the level surface?
Mm-hmm. Yeah, so what about that? Like, why is that true?
Yeah.
So, where is that thing? I have a ball somewhere. Hold on. I know I have a ball. Well, the goal here, so the idea is, yes, I have 7 million. I'm going to get a prop. Hold on. Let me get a prop. Where is it? Cool. I promise this is important. So I have this ball here. It's a really good for trigger point therapy. If we need one of these, definitely use it. So what is the idea again of the gradient? And I think this is a really important point, the difference between a two-dimensional gradient and a three-dimensional gradient. A two-dimensional gradient, as we've seen, right, in the past, tells me the following. If I have a function that is something like z is equal to f of xy, right? I have something like this. I have z is equal to f of xy, if I do this. And if I go ahead and do this, and I compute the gradient here, this is going to be a two-dimensional gradient. I hope we all agree on that. The gradient of fx and fy. And so what does that tell me? That tells me that if I want to go in the maximal rate of change, right? If I want to go in the direction, if I'm here and I'm trying to figure out which direction to go in, I calculate this and it tells me which direction I need to face and walk in to have my height increase the fastest. And again, we realized that if I have level contour plots, if I have contours like this, right? If I have contours and I'm here, I know my gradient is going to be orthogonal to that, right? It's going to be orthogonal. Any single place that I go, it's always going to be orthogonal here to the contour lines. And so these are level curves, right? These are where I have f of xy is equal to k. F of xy is equal to k. Now, what I'm going to do here is I'm just going to, as an example, I'm going to take this. So this is actually an example I did last time. What I'll do is I'm going to take my function f of x, y, z. I'm going to name this x squared plus y squared plus z squared. Okay? Now, if I just take the function x squared plus y squared plus z squared is equal to 1, what we all agree, think about what this is. I hope you would agree that this is a sphere of radius 1. Let's assume, without dropping this is a sphere of radius 1. Okay? Now, this is now a level surface. This is a surface. And again, you know, what I'm doing here is I'm trying to see, okay, I have a level curve here. A level curve tells me where f of xy is equal to k. Just some number. Where's f of xy equal to k? Here what I'm doing is I'm saying, okay, I want f of xy, more specifically, f of xyz, to be equal to 1. Which now this is a level surface because I'm dependent on 3 variables. And again, what I could do is I could take the derivative, I could take the gradient of f here, and I hope you'd agree the gradient of f is actually pretty quick, which is 2x, 2y, 2z. Right, just kind of calculating that pretty quickly. Now, what does that look like? That looks like, if you kind of imagine it, right, in a two-dimensional sense, if I took the vector xy, well, the vector xy is just the point going from the origin to that point. It's going directly away from the origin, wherever I'm at. And so similarly here, this vector here is again directly away from this. Like that. It's directly away. And why is that the case? Imagine if I had another ball that was bigger than it, right? Maybe f of x, maybe a radius of 2. Think about that. This is when maybe then f of x, y, z is equal to 4. Maybe there's a ball above it. My goal then, in the idea of a level surface, just level curves in general, level surfaces in general, is to figure out, okay, if I am at this little ball, and I want to get to the bigger sphere outside of it, which direction do I need to go in to get to the bigger ball? And the way to get there is literally just directly away, which is exactly orthogonal to the surface, which is normal to the surface. And so it actually is the same exact idea that the gradient vector will still get you the maximal rate of change. It will get you to the next level surface. It will get you to the next level curve. It's just depending if it's a one-dimensional or two-dimensional object. And so therefore, because of that, the gradient has a lot of really interesting things. And specifically, it could tell you the normal vector to a plane on a level surface. And that's what this kind of gives you, just in general. And I hope that makes maybe more sense now, the difference between like a two-dimensional and three-dimensional gradient. They're the same exact thing. They honestly are. They're exactly the same. I've just added a third dimension, and that gives us actually a lot more interesting stuff based off of that. I hope that makes sense. Let me know if I need to clear anything up, because I at least on that end, because I find that that's a really important point and distinction to make, and it might take a little while to sink in, but that's the difference there. It's kind of coming back to what the gradient actually means, and if there's anything else you would be asked to find the gradient of. The normal line, right? The normal line to a plane to any surface. The direction of the gradient is the direction vector, right? So if I want to find the normal line specifically is the line that is in the direction of the gradient. So if I had my surface here, like this, and I wanted to find the normal line to this, I know the equation for my line, right, is equal to r of t is equal to r0 plus t times v, something like that, down here. And I know the direction of my direction vector, my normal line, the direction vector, is the line that honestly goes right, that is normal to the surface, right? So the direction it's going in is the normal vector, which is the gradient. So this right here will be the gradient. And this right here is just a point on the line, which here, I know my point on the line is going to just be 0, 1, 1. And so what I could be asked there maybe would be that this would just be 0, 1, 1, because that's my point, times t times my gradient vector, which is 1, 0, 1. And so this could be the equation of the normal line, for instance, here, and kind of you could do stuff with it. So that's maybe at least what I would suggest thinking about for the gradient. I'm trying to rack my brain about what other things they could ask you for. I'm kind of thinking that would be at least basically it. Maybe they would ask you more of a, directional derivatives. Like directional derivatives are highly dependent on the gradient. If you see maybe something like the maximal rate of increase or the maximal rate of decrease are just the direction of the gradient, and the opposite direction of the gradient, so the negative of that, those are the directions of the gradient. Those would be the maximal increase or decrease. Yeah, that would kind of be it that I could kind of think of, at least off the top of my head. They can come up with some fun problems, so I don't really know everything about that, but for a 40-minute exam, probably that's at least what I would suggest thinking about. It seems like they're going to go a little more conceptual, at least with this. I'm not too sure, but it seems like maybe they'll go in that direction more. They're kind of trying to test everything as possible, because it's very tough to test everything in chapter 14 in 40 minutes. So we had to try to get as much information as possible. So we can hope that we can get into that. Any other question about the gradient here? Because I would like to go over the chain rule in the next here.
I do have one question. Where is is there solutions for this posted?
Solutions for?
Yeah, practice problems.
Yeah, so they all should have been posted. I know. DJ stuff. The solutions are on Piazza.
Okay.
I think it's on question number 104 or something like that. And then I've also sent all of my solutions out to all the other TAs for my one that I came up with. If I'm not mistaken, yeah, so that's at least there. I know that DJ did post them, or maybe they're on. Yeah, I know they're on Piazza at least. Yeah. I don't know specifically how many questions there'll be. I'm assuming there'll probably be like 4 to 6 questions. I'm assuming. I think that seems fair.
This morning in class, he said there's going to be 5 questions. They're going to have a couple parts each.
Great. So that I was right in the middle. Excellent. So it'll be 5. That answers your question. Cool. Thank you.
I have a question. So for the practice worksheet for the mini exam practice problem, I don't see like a solution to that worksheet.
The practice exam?
Yeah.
So they're all in the they're all in the problem. If you're looking at discussion section 31's thing, they're in the study guides mini exam folder. So they're all there, all the answer keys to that.
Okay. Cool.
Yeah. So if you're looking at solutions, all the solutions are on Piazza too.
Okay.
Oh, yeah, I don't have those on my Canvas because I guess I have Alexandra as my TA.
So okay, got it. So on Piazza, they should be on there. If you can't find it, let me know, and I can kind of highlight that too. Okay, so I would like to see. I know that Owen, you had asked to go over the chain rule. What about the chain rule specifically? Are you just a chain rule problem? Do you want to do the implicit function theorem? Do you have a problem in mind?
One second. You can go to something else. I had a problem. I just need to find it.
Okay, not a problem.
I had a question, Nick, actually.
Yeah, Simon, go for it.
When do you use like a partial versus like an actual D when you're in? I always get that confused.
Yeah, good question. This actually could lead us right to the chain rule. So the difference there's a subtle difference. I'm honestly not sure if they'll be taking off for that, but it's just a pretty important thing to just kind of remember here. So I think you're kind of thinking about the difference between this and this, something like that.
Exactly.
When do I use which of those? So if I tell you that a function is dependent on a single variable, then I use the letter D. If it is dependent on more than one variable, I have to use the partial derivative. That's the difference. So if I tell you that I just have a singular variable, I can use the English language notation, just as for a D. If I have more than one variable, I have to be very careful with that because I have to tell you which derivative I'm taking, just in general. In the same exact way, like I could tell you here f prime, and you would be, okay, I know what that is. If I told you f prime here, you'd be like, what? Right, that doesn't really make sense. So I kind of have to use that, that inverse notation, that f sub s maybe, or f sub t or something like that. It has to be kind of changed. That's the difference between those two notations and why you would use one and then the other. Yeah.
Thank you.
Yeah, no problem. So I mean, at least the idea of the so nobody has any other, at least the general.
I have a question really quick. So there was a question on the last quiz. I think it was number 3, at least on my quiz. It gave you like it was xy tan of z minus y equals 4z, and then it wanted to know the partial of z with over the partial of y.
This guy?
So I know there's that that formula, like partial of z over partial of y equals like negative fy over fc.
Yes.
They also gave you, I think, or no, that's just when you do the
That's the implicit function theorem.
Yeah.
Yeah.
So does that go for all things? Like if it was what is the partial z over the partial x, and it would be negative fx over fz, just like
Correct,
it's flipped
correct.
with the negative. Okay.
Yeah, exactly. So that derives itself from, that actually derives itself from the chain rule. So just to kind of show you where that kind of comes from, this very quickly, we can do this actually really nicely. If I told you that I have a function of x, y, f of x, y, and z, and it's equal to 0, something like this, and I told you that z is a function of, is dependent on x and y. Well, and I wanted to find, for instance, dz dx, let's say. What I could do is I could think about the chain rule, and this is actually something you should do for almost every chain rule problem. What I should do here is if I wanted to take the derivative of each side here with respect to x, well, think about what I'm doing there, right? I tell you that f is dependent on 3 things. F is dependent on x, y, and z. I hope you'd agree that x is dependent on x, y is dependent on y, but z is dependent on 2 things. It's dependent on x and y, right? It's dependent on both of those. So if I want to take this derivative with respect to x, what I need to do is say, okay, well, if I want to take this derivative with respect to x, I kind of start from the bottom and I see, okay, what's dependent on x here? This guy and this guy, right? So what I could see there is, okay, well, if I want to use the chain rule, wherever I have overlap in the middle terms, in this row, wherever I have overlap, I want to do a multiplication. So the derivative here, if I take this whole entire thing derivative with respect to x here, you can even make this a k if you wanted to. You can make this just any constant because the derivative of a constant is 0. What you can do is this would then be the derivative of f with respect to x, needing to use partials because f is dependent on 2 variables. Then multiply it, because this intersection right here denotes a multiplication, by the derivative of x with respect to x. We'll talk about what that means in a moment, but you just gotta think about what it means. This last guy here, I know that y is not dependent on x, so I don't have to worry about it. This other guy over here is dependent on x because I see f is dependent on z and z is dependent on x. So I can write that df dz, and I multiply this by dz dx. And this is equal to 0 because the derivative of k is just a constant. And so if I want to find dz dx, okay, I have that. But what is dx dx? Well, what is the derivative of x with respect to x? Just 1. So this becomes 1. And what I'm going to be left with, I'm going to be left to df dx let me actually scratch that for a second, plus df dz times dz dx is equal to 0. And again, if I solve this, right, what I could do is I could just subtract over the df dx and then divide over the df dz, and I would get my implicit function theorem. Negative, because I'm going to subtract over, f sub x, because this is f sub x, divided by f sub z. And this works for anything, right? If I did df dy, right, if I took this derivative with respect to y, this whole entire thing would work out the exact same way, except this would be dy dy, this would be dy, and this would be dy, so I would get the same exact thing. And so therefore, that's how I use the implicit function theorem. So if I'm going back here to this problem, just kind of just looking at this very briefly, just kind of doing this out. The thing you need for the implicit function theorem is to make sure you have all of your functions on the same side to do this. So what I'm going to do is I'm going to subtract over 4z. I get that. And then now this is my function f. I'm going to name this entire thing f. And then my function dz dy is going to be equal to negative f sub y over f sub z. It's just taking the partial derivatives of this function specifically. So taking the partial derivative of this function with respect to y, I'm left with x times tan of z. Negative out in front, make sure you add a negative. Tan of z minus y, 1, because the derivative of y is 1, divided by the derivative with respect to tangent, with respect to z. What's the derivative of tangent? Secant squared. And then we would have minus a 4. And just don't forget this minus sign out here. You don't have to go through if you don't want to. You can leave it at that point. And this allows you to kind of simplify things greatly. You don't have to go through, complicated implicit differentiation, it really simplifies itself much more. So that's kind of the idea for this.
I have
So that
another
is-
question.
Yeah.
Oh, sorry, I think someone else was saying something.
Oh, did somebody else, was there somebody else asking a question there?
Yeah, I was gonna ask, is there a time that you can't use this like formula? Like it doesn't work?
Well, that is a very high level question, because that takes us into something we're going to assume you can.
Yeah, I don't really, just like for the exam, is there gonna be a time
Yes,
for it?
yes. Please use it. If they give you if they give you a time that you can't use it, yeah, don't worry about it. I'm yeah. You're allowed to use it if everything is continuous and nice, then yes, you're allowed to use it. It's kind of the same thing for Chloros Theorem.
Okay, thank you.
So if you have continuity, you can definitely use it.
Should we only use it for if it asks to use implicit theorem function?
No, you can use it at any time.
Okay.
Definitely use it at any time you want. They would not restrict you on that end. They would actually they would not tell you to not use the implicit function theorem. That would be very diabolical.
I know there's the other chain rule formula, and that's usually when we're given like a larger formula that includes like x, y, and z, and then we'll get like smaller functions for like x equals something with like t in it or s. Is that's when we use the different formula where it's like partial f over partial x times like partial x over partial like z or whatever letter you're looking
stuff
for.
like that. Yeah, so that comes from your trees that you draw. And I would highly suggest you kind of just think about them in terms of trees there. And what do I mean by trees? As a person that really likes plants and likes graphs and all that. So just kind of thinking about what this means. If I have some function here, right? One problem that I think that is a really good problem that I wouldn't put past them to ask is if they give you just a very general thing. Like if they ask you, for instance, okay, assume I have a function, x, a function of x, y, and z, which is equal to w, something like that. And then they tell you that x is dependent on g of st, y is dependent on h of st, and z is dependent on another letter st. You see here. Kind of like that. Then, what can and then I ask you the question, how do I calculate dwds? Right? That's actually, a very general question, but you can write down a formula for it, right? And how can you do that? It all comes and stems from just in general, it stems from your tree that you draw. So what do I mean by a tree? W, that's the top function I'm worried about, right? This is the top function I'm worried about. It's dependent on three things: x, y, and z. Dependent on three things. I know that x is also dependent on s and t, y is dependent on s and t, and z is dependent on s and t. And so if I want to figure out what dwds is, well, I know here, what I want to do is I want to circle all of the connections with s in it and continue to go forward and all the way up until I hit the top function. Wherever I start off here, each one of these individual branches is going to denote an addition. As well, each one of these intersections here in the middle is going to denote multiplication. So just kind of as a kind of a, how do we do this? Well, we kind of think about, okay, dwds, every single one of your things you write should look almost identical to if I'm kind of just splitting it up. So for instance, this one right here, I see this branch right here can be written as dw dx. And then I know that dx is dependent on ds. Note here that I have to use partial derivatives every single time because x is dependent on s and t, and w is dependent on more than one variable as well. And if you note here, if I canceled out the dx using horrible notation and horrible fraction work, it looks exactly dw ds. That's how we should kind of get back to it. Similarly, this middle branch is going to tell me dw dy, and then dy ds. Again, if I cancel out the dw's, I'm going to get that same exact thing again with dw ds. And lastly here, dw dz, this last branch, dz ds. And so if I want to calculate, how does w change with respect to, s here, right? I can write this out without even knowing. And that's what you should be able to do, genuinely. Because a lot of times you might get some really funky things. Maybe y is dependent on more than one variable. Maybe z is dependent on more than one variable. Maybe it goes even deeper. I honestly just did, in my research, I just had a chain rule, got a problem like this that was dependent on like 5 rows of this. So you need to be very careful when you're kind of computing the chain rule over and over again, and making sure that you understand and you know what's dependent on what specifically. And so from there, what you can do is you can just calculate dw dx, dw ds if you kind of do that. So that's what I would suggest doing. I think this is a very reasonable question to ask, or to write down literally this, and to be able to draw out like a tree diagram like that. I think that's a good way to know that you know what the chain rule is. Making sure you kind of draw the schematic out. Yeah. There. Okay, that's kind of that. Does anybody else have any questions? Any other questions that I could answer?
Could we do the question 4 from the posted quiz 4? It's the chain rule of y ln xy, and then it has gst is equal to f t squared minus 3s. All right.
Oh yeah. So say that again. So you have your function f of xy
is equal to y ln xy.
Mm-hmm.
And it said, and suppose g of st is equal to f t squared minus 3s and negative 3t plus 7s. And it's at gt is 1, 2.
Okay. So there's a problem for some people's quizzes. Here, I don't know why my marker is so faint. I find this really, really bizarre because I don't know how I'm losing marker.
Yeah, I was gonna say, is there a way you can make it thicker?
This is so this is really, really, really strange.
Is it that red box with the at the top, the toolbar at the top?
Which red box?
At the toolbar, the top right corner of your screen, is it there?
Oh, this guy?
Yeah.
No, that's actually my YouTube extension. So I appreciate that though. I actually don't know why this is being so weird. This actually happened last time too. I don't know if it simulates your marker dying.
Well, it might be a zoom issue. If you were to zoom,
I think you have to zoom in.
and then
if I zoom out like this, we can actually visually see that this is actually getting visibly like. If I zoom out, I'm not zooming out on yours. Like.
If you zoom all the way in, it's probably really thick. And then you can just start at a new.
Where is everything? Hold on. I am so confused at the moment. But like if I scroll out here, it gets more and more and more. Okay, hold on. Yeah, I see what I'm doing. Let's try this here. I see. Okay. Yeah, I'm being it done. Sorry.
Want me to reread it?
I think I remember it. So it was y. That's probably better. Yeah, I hope that's better. F of xy is equal to y times the natural log of xy, and you were told that g of st is equal to f of t squared minus 3s, and then negative 3t plus 7s, and I'm trying to find gt of 1, 2. Is that correct?
Yes, that's correct.
Okay, great. So I don't know why I was doing that. I'm sorry. I realized what my issue was. I was too zoomed out. You're absolutely right. Okay, so what I'm going to do here is I want to kind of think about what this actually is saying, right? So the first thing I want to realize is my function f here is dependent on x and y. As well, f here, we see that g is dependent on s and t, and it's equal to f at t squared minus 3 and negative 3t plus 7s. So we kind of note that x here is going to be equal to t squared minus 3s, and that y here is going to be negative 3t plus 7s. Like that. Okay, so we see that x is dependent on s and t, and y is dependent on s and t. So we can kind of write this out and say that, okay, well, I have my function f, or actually I have my function g, maybe more specific. G here is a function of x and y, because we note here this is actually kind of a function of x and y. Right? G is dependent on x and y here, which are also dependent on s and t, and are dependent on s and t as well again here. Because G is a function of f here, and this right here can be considered x, this right here can be considered y. And so we can kind of go backwards and kind of rewrite this in some way. So if I'm trying to find g sub t, which is the derivative of g with respect to t, we again can write our chain rule, kind of circling our goals right there. And so if I want to find GD, GT, we can find here that this really is going to come out to being, well, this is really a function of f here. So this is really going to be, the function of f with respect to x multiplied by dx dt, the same way we had in the past, plus df dy and dy dt, because of these this tree that we've drawn. And so what I now admit here is we're now going to just calculate each one of these at the point 1, 2. Now, let's calculate all individually. Let's calculate f sub x. F sub x here is going to be just equal to y divided by xy multiplied by the derivative of the inside there, which is y. Right? It's the derivative with respect to x, which is just y. So this becomes actually y over x. Similarly here, f sub y is going to be equal to, I do this product rule here. This can be the natural log of xy, because the derivative of y is just 1, times the derivative of the natural log of xy. So I'm going to have y divided by xy multiplied by the derivative of xy, which is x. And so as we can see, this is going to be just equal to 1. So this comes out to the natural log of xy plus 1. Okay? Similarly up here, we have that dx dt, actually it's pretty nice, it's just 2t. And we have dy dt, which is just equal to negative 3. Now, I want to kind of go back here, and I want to now calculate fx, fy, dx dt, and dy dt at my point. And what is my point, right? I have that this is 1, 2. And so kind of looking back this means that s is equal to 1, and t is equal to 2. So I also have an issue down here though, because my fx and fy are dependent on x and y and not s and t. Even though x and y are dependent on s and t, so I can find what the values of x and y need to be by plugging in t and s into this formula up here. So x at 1, 2 here is just going to be equal to, I would get 2 squared minus 3 times 1, which is equal to 1. And then y at 1, 2 is equal to negative 3 times 2 plus 7 times 1, which is also equal to 1. And so therefore, my point that I'm kind of worried about is at point 1, 1. And therefore, I can find that fx at 1, 1 is just equal to 1 over 1, which is 1. And fy at 1, 1, I hope you'd agree, is just the natural log of 1 plus 1, which is also equal to 1. As well, up here, I'm kind of going down. Up here, with my derivative with respect to x and with respect to y, we see that dx dt at the point 1, 2 is just equal to 4, right, because t is 2. And also dy dt at 1, 2 is also equal to just -2, -3, because there's not really anything there. And so therefore, I've kind of already portioned this out, but this guy right here, if I want to find what dg dt is at the point 1, 2, df dx at 1, 2, as we found here, is equal to 1, times dx dt, which is equal to 4, plus df dy, which is equal to 1, times dy dt, which is equal to -3. And so therefore, this just admits that this is equal to 1. And so what did we do? Kind of just going backwards here. We wanted to find that dg dt, how is the function g changing with respect to time as I move through my time? Especially with respect to this t, instead of s. Well, I know that g is dependent on two things. It's dependent on x and y, because it's dependent on f. And f, which is dependent on x and y. X and y are both dependent on s and t. And so I know that if I want to use the chain rule here, I can draw my tree diagram and note that I'm going to have to use multiplication here. So dd dx, dx dt, plus dg dy, dy dt. Kind of written it like this, using the f here because we know that f is kind of the function we're trying to worry about mainly. And then calculate dx dt and dy dt, and df dx and df dy. Plugging in my points. And this is kind of sometimes where some people trip up. You know, if you're given the s is equal to 1 and t equal to 2 like that, you can go through your channels and actually get what x and y have to be. And so that's usually the problem that some students have had in the past, is kind of not realizing that, to kind of use that here. And then from that point, you're just going to multiply it out and it's equal to 1. And that's kind of the idea just in general. Does that make sense? Anybody have any questions about that process there? Okay.
All good.
Cool. All right. So any other questions that I can answer? Anything else you'd like me to talk about at all here? My recommendations for, if nobody has any other questions, I can kind of just talk about here. When you're studying here and you're kind of doing problems, always in math, you know, make sure it's a participation sport. And make sure you're doing problems, and without the aid of your notes for the most part. Make sure you go away from your notes for a while and kind of just do problems on your own, and just kind of just work through them. And try not to memorize if possible. Right? Don't kind of say, oh, I've seen this exact problem, I'm going to do the exact same thing. Think about why at every single step. Right? Why are we doing every single step here? Why, if you cannot answer that why there, that's something that's really important that you're missing. Right? The why is it's very, very important. It's more important than the how. How is really important. How to do problems is really, really important concept, and procedurally, you need to know how to do them. But, so you don't have to memorize it, the why is much more important too. Right? So why did I have to go through this, right? Every single step here. If I want to find g sub t, I had to then use the chain rule. Why did I have to use the chain rule, right? The reason was that g is dependent on x and y are dependent on two other variables too. They're dependent on s and t. And so to kind of understand how g changes with respect to t, I need to know how g changes with respect to x and how x changes with respect to t, and similarly for y. And then I would have to calculate each one of these. Right? And why do I have to do that? Right? And how do I do that? Right? Why did I have to take s equal to 1, t equal to 2, and then go up here and kind of plug in x and y and try to find out what x and y are depending on what t and s are? Like, why did I have to do that? Well, I needed to find what fy and fx are. I needed to do that. So I needed to find what the partial derivatives are at those points. So I needed to plug that in and kind of come back here. And then kind of also think about the interpretations of things. You know, once you get your answer, once you get your answers to a lot of these problems, what is the interpretation here? This says that as I change with respect to one of these variables, time, this means that the function is going to be increasing by a value of 1 as I move in the t direction, whatever that physically means. I don't know what that physically means, but it exists something. So that's at least my suggestion. Always know the why, because that also helps you not memorize. And then when you look at a problem, you go, oh, I haven't seen this type of problem before. Well, you don't have to think about your memorization techniques. You're going to think about, okay, what does this physically mean? What do these things mean? Why would I do something like this? Where have I seen this before, maybe? And what did I do here, and why did I do it? Right? And then kind of go from there. That's at least my suggestion. Any other questions that I can answer? We still have like 9 minutes or so. I can
Yeah,
answer.
I have a question.
Sure.
So this, I'm looking at your practice mini exam that you had given out. So on 3A and 5B, they're both asking for the equation of a tangent plane.
Correct.
But they seemed, I guess I'd gotten one of them wrong because they were solved differently on the answer key. The 3A was solved like a L, X of Y, and then the other one, my point is in 5B, it didn't seem that you used the height, and in the other one you did.
You mean the 1/2? Specifically?
Yeah, or it was more so in like 5B, they were just like solved differently, but they seem to be asking the same question.
Well, they absolutely are. You're right. They're asking the same exact question. And why is that? I guess why is the difference? What is the big difference there?
Yeah.
The difference here, honestly, you could solve them using the same exact technique if you wanted to.
Okay.
You could solve the same exact thing. So what I could do, if I wanted to, is I guess in this one, I utilized the linear approximation formula. Right? But what I could do instead is, in this case, right, what's the difference between this equation and this equation? This equation here, I can actually get something z equal to. Right? I can get z is equal to a function of x and y.
Yeah.
In this one, I can't. And so in order for me to solve for the tangent plane of this, I have to use kind of the gradient method to find my normal vector. Because I can't actually get something as z equal to. And so I can't just take fx and fy and kind of use that formula. Up here, I could do the same exact thing if I wanted to in the same way. So I could subtract over the z and solve for the gradient in that same way. I don't know exactly how I went about it because I know there's two different ways that you could go about it. But yeah, what I did here is I just used the linear approximation formula.
Mm-hmm.
What you could do instead if you wanted to, which is a very valid way.
I tried to use the linear approximation formula for 5B.
Yeah.
I basically ended up having an extra 4.
Yeah, so the reason why is you can't do that because the linear approximation formula is only for if I have something z equals.
Okay, that's what I was missing.
Yeah, so if you can't do that, if you can't get z equals, you have to go through, because this actually is like a level surface. So it's really a function of x, y, and z is equal to 0. You can do the same exact thing up here that I did down there. If you wanted to, so I have something z is equal to x e to the x minus y, something like this here. And what was the point again? -1? Oh, it's just -1, -1, -1. Something like that. What I could do instead is I could actually subtract over the z. And I can define this function as an f, which is dependent on 3 variables, x, y, and z. And it's equal to 0, right? It's a function of 3 variables equal to 0.
Yeah.
And so what I could do instead, if I want to find the normal vector, I could just take the the gradient of this. I wanted to. And the gradient of this here is going to be just using product rule for x is going to be just e to the x minus y plus just x e to the x minus y. The derivative with respect to y is going to be -x e to the x minus y. And the derivative with z is going to be this -1. So you're always going to get a -1 there, always if I just have a z, which is kind of nice. And so if I find the gradient here at -1, -1, -1, I'm going to get, again, if I plug everything in, I'm going to get here, I would find that this is going to be, 1 minus 1. This right here is going to be just a 1, and this is going to be -1. So this whole thing is going to be 0. And so from there, I could then utilize the fact that the gradient of f is my normal vector and get that 0, x minus x plus 1, plus 1, y plus 1, plus -1, z plus 1 is equal to 0.
Mm-hmm.
y plus 1 minus z minus 1 is equal to 0. And this again gets me z equal to y,
Okay.
which is the exact same thing as I got last time. So honestly, you don't have to memorize the linear approximation formula. And honestly, you don't have to. You can always just go and just use the gradient as your normal vector if you want.
Okay.
That's actually something I would suggest doing. And just noting that for a linear, if you're asked for a linear approximation, you do need something of the form like z equals.
Okay, that's part I was kind of like missing.
Yeah. So the reason why, if you're kind of thinking about, if I have a linear approximation, kind of like yeah. So it just asks here for the equation of a tangent plane. So you can write it any way you want. But if I want to use this to approximate a value, I know z is approximately this value. So I need something z equal to use that.
Mm-hmm.
Down here, though, I'm just asking for the equation for a tangent plane, too. So I'm not really finding a linear approximation. Yeah.
Okay, thank you.
No problem. Yeah, this was a different practice test that I made, and I gave all to all the TAs too. And I think I posted on Piazza. I might not have posted on Piazza. I just sent it all to TAs and asked them to kind of post them. I'll post it on Piazza though, right afterwards. So those of you who don't have it, I'll do that. Yeah, I'll do that too. Yeah. Okay. Any other questions here that I could answer? Anything else here that I can talk about? Okay. So I guess just overarchingly, right, what are you going to want to kind of hone in on? You know, one thing that I told my students, at least which I sent them an announcement today, and one thing that DJ has kind of emphasized to me is don't also think about, you know, the practice quizzes and practice exams and all that, the midterm mini exams that we've made and study guides are a really good way to, as a resource, but just also remember that, you know, you might not see exactly the same things that you see on these practice exams, right, or anything like that on these mini exams or these midterms. The big overarching things, and that's why I always suggest you understand the why, because this allows you to make sure that you know how to solve problems that might be a little bit more foreign to you, that you really haven't tackled, but you can tackle them with the same techniques that we've had. So make sure when you're studying tonight, hone in on what you really need to know. One technique I always like to do is pick a topic, say gradient, or tangent plane, or partial derivatives. Write as much as you can about that, anything, how to compute them, what they are physically, even make up an example if you want for yourself to do it. Write that down for like 15 minutes until you can't anymore, and then go back to your notes and visualize and see what you made mistakes on, what you forgot, and what you know. And all of that information now is to the front of your brain. That's actually how I studied all the time. And I still study today when I still have exams. It's really important that the more that you can, you know, visualize what you don't know is really important. Knowing what you don't know is a really good thing, and a really good sign of somebody who's really thought about this a lot. And if you know what you don't know, you can at least tackle that and try to figure things out. If you don't know how to do a big problem, if you don't know how to solve a problem, there's a smaller problem that you need to solve before you can do it. So keep honing in. What don't you understand about this problem? Oh, I don't understand, you know, why I need to use the implicit function theorem here. Go to the implicit function theorem and understand that, and then go back to the problem and kind of solve it from there. I don't know why, you know, I need to use the gradient here. I don't know how to calculate gradient or something like that. You know, every problem, bigger problem, can be solved with solving smaller problems. So that's at least my suggestion there. Okay, it is 6 o'clock. I'll stick around for a little bit more if you have any questions. Yeah, so thank you for coming. I'll post this whiteboard too, even though it's a little bit faint on the other side, because I was being very silly and making, yeah, I was drawing way too big, I'm realizing now. I didn't realize how zoomed out I was getting. So I'll post this regardless, and then I'll also post my practice exam too, for those of you who don't have it, with the answer key. And yeah, okay. Well, thank you guys for coming. I really appreciate it. And if you need anything else from me, let me know. I'll be around. And yeah, I'm gonna hang up, and I'll also post this review session on YouTube too. Hope you're doing well, and I will talk to you all soon.
Thank you.